Okay, let's finish up chapter 8. Today we're going to cover that last page of notes. We're going to look at intermolecular forces and liquids. So we've been talking about bonding a lot, and that is the forces that hold atoms or ions or metallic atoms together. But especially when we're thinking about a covalent compound, what holds those discrete molecules together, or in an element, what holds atoms together, right, in solid and liquid phases? And that's intermolecular forces, right? So your intermolecular forces are going to be the attractive and repulsive forces between molecules. There are different types of intermolecular forces. Some are stronger, some are weaker, but something to note is that bonding forces are always going to be the strongest, right? So these forces we're going to talk about today are not going to be stronger than your covalent and your ionic bonds. We're going to look at London forces, dipole-dipole interaction, and hydrogen bonding. So the London forces are the weakest, then dipole-dipole, and then hydrogen bonding. This is going to be important to keep track of because this is going to allow us to make predictions about properties like boiling points, vapor pressures, surface tension, etc. All right, I will often use IMF to abbreviate intermolecular forces. The first one that we're going to look at is the dispersion force, or London forces. It's just two different names for the same phenomenon. All atoms and molecules are going to experience London forces. We tend to talk about them more with nonpolar molecules, or atoms, because that's the only force that holds them together. But it's important to recognize that it is common to all molecules. Now, let's discuss what this means. How can we have an attractive force between two non-polar substances? Well, when we think about what an atom or a molecule actually looks like, even if we don't think about it as being of having a negative or a positive side, we do know that in the atom there is an electron cloud. In the molecule, you've got your valence electrons, right? Your electron cloud. And they're moving, they're constantly moving. So in a given instant, more of your electron density might be on the left, which would make the right a little bit electron poor, right? This is temporary, this is fast, but this is a dipole, right? A separation of charges that does occur in even your most nonpolar scenarios, like with the helium atom or the H2 molecule, where there's no electronegativity difference. So these instantaneous dipoles can then affect the neighbors, right? Because this helium is also an electron cloud. And what's going to happen if its neighbor has a momentary positive charge? Well, the electrons in this HEB are going to be attracted, right? And so it's going to induce a dipole in the neighbor. You see the same thing happening over here. Say H2 is perfectly balanced. If the neighbor has an instantaneous dipole, the electrons are either going to be attracted to the positive side or repelled by the negative side, and you will get an induced dipole. So then when you have these little instantaneous or temporary partial charges, you are going to get an attraction between the positive and the minus and the negative sides of two different atoms or molecules. This is going to be additive, right? So something called polarizability comes into play here. Let me make sure I'm not skipping. Okay, polarizability is pretty much a measure of how much a dipole could actually really occur. And that is going to be directly related to size. The larger an atom, the larger a molecule, the more electrons you have, and the more space you have for them to spread out. So we're going to find that Larger atoms are going to give us stronger intermolecular attractions than smaller atoms. We can even see this when we look, and I'm going to skip ahead here to some pictures I've saved. We can see that when we can compare boiling points. If we compare just down the noble gases, helium to radon down here, they're all neutral, they're all unreactive, they have a full valence shell. The only difference is their size, really, and you can see the boiling point increasing as we go up in size. If we think about covalent molecules, kind of focus in here on this picture, methane, butane, hexane, and octane are all carbon chains surrounded by hydrogens. They're considered very nonpolar. The CH bond is not a very polar bond because similar electronegativities, everything's very symmetrical, everything's very balanced. So there's no real polarity to this molecule other than those temporary and induced dipole moments. So when we compare boiling points, right, the boiling point of methane is minus 164, and by the time we go up from 1 to 8 carbons, the boiling point's now 128 degrees C. Right, it's a big difference, and it's all based on surface area, size, the ability to have these temporary and induced dipoles, right? There's more potential for interactions between the molecules, which means it's going to take more energy to pull them apart, and that's what happens when you go from liquid to gas. All right, so everything experiences dispersion, or London forces. Next, let's look at dipole forces. Dipole forces are going to be the major attractive force for polar molecules. So if we think about, if we think about the HCl bond, right, and the HCl bond we know is a polar bond. Very different electronegativities. Chlorine is going to be more electronegative than hydrogen, so you are going to get that partial negative on the chlorine, a partial positive on the hydrogen. Now this is a permanent dipole. Permanent, right? It's not induced, it's not instantaneous. This is always going to have this imbalance in electron density, with more negative on the chlorine, leaving more of a positive charge on the hydrogen. What is that going to do? That is going to, for one, cause a little bit more order, even in a liquid, between your molecules, because you are going to want to maximize the attractive forces and minimize the repulsive forces. So you notice the chlorines start lining up with hydrogens on nearby molecules, and there's going to be an attraction between that negative and positive charge. That is a stronger attraction when you have a permanent dipole than when you have a temporary dipole. That's why this intermolecular force is stronger than the last one. You see this, it's very easy to see here with a kind of a simple little 2-atom molecule. This applies to any polar molecule, and you will have larger polar molecules you might be asked to look at. So if we think about something like chloromethane, this is a tetrahedral molecule. The CH bond, again, not very polar. And so what you're getting is on one side of the molecule, you're not getting any pull of electron densities, but out towards the chlorine, you're getting a pretty strong pull. So you're going to see that on this side of the molecule on this side of the molecule over here, you are getting a pretty negative partial charge, right? So then on the other side, you would get a partial positive where all the hydrogens are, right? And so you have those two sides of your molecule. And again, all of your chloromethanes are going to start to line up to minimize repulsions and maximize attractions. before we do any more comparisons, I want to go into the last intermolecular force covered in this chapter, and that's hydrogen bonding. There's a few things to note here. It's the strongest of the three. It is not actually a bond. It's still just an intermolecular force, so the name is a little bit misleading. And it really is just a dipole-dipole interaction, but it's a special dipole-dipole interaction. For hydrogen bonding, we are looking at hydrogen, let's switch back to the pen. Hydrogen bonded specifically to O, N, or F. These are our most electronegative elements, and hydrogen only has one electron. So when a hydrogen is bound to O, N, or F, it is almost like you have this exposed proton. It's a very, very strong partial positive. So if we looked at an OH, right, you're going to have a very strong partial positive there, and then, of course, the negative on the oxygen. Let's see. I thought I had a different picture. Okay, that's okay. Here we go. So what do you need for the hydrogen bond? It's a hydrogen on an O, N, or F, not just on a molecule with O, N, or F, but directly attached. And then it is going to be attracted to the lone pair of another O, N, or F. Right? So if I could switch this over here, right, you're going to have that attraction. Now, on either side, right, this atom right here could be an O, an N, or an F, and then what it's attracted to could be an O, an N, or an F. So you could have, let's show this really quickly here. You could have, and maybe I'll come over here. Here we go. You could have, for instance, an OH that was hydrogen bonded to the lone pair of a nitrogen, right? As long as the atoms on either side, the side with the covalent bond and the side with the hydrogen bond is both O, N, and F, then you can have a hydrogen bond occur. So from there, let's look at a comparison. All right, we know that hydrogen bonding is the strongest, dipole-dipole next, and then London forces. And we know that they're all weaker than an actual bond. So if we compare diethyl ether, butanol, and this ionic salt, we should be able to accurately predict the order of the boiling points, right? The diethyl ether experiences dipole-dipole interaction. You do have that oxygen that's going to pull more electron density away from the carbons. So you will have a portion of the molecule that has a permanent dipole. The alcohol has the ability to hydrogen bond. Remember, the hydrogen has to be directly attached to the oxygen. And then here we're looking at an actual ionic bond. And we see the difference reflected in the boiling points. The dipole-dipole interaction is the lowest. The one that can hydrogen bond is significantly higher. And the one that we're looking at an actual ionic bond, that's going to be much higher, right? Ionic bonds are much stronger than these intermolecular forces. All right, one last property to look at, or one last picture to look at before we move on, is how hydrogen bonding affects our properties of water. So water is a very small molecule, right? So the London forces aren't really going to be they're going to be present, but again, it's a small molecule, so they're not adding up, but it can hydrogen bond, and every single atom can be involved in a hydrogen bond. Most substances, when they solidify, right, are going to be more dense, but we know that's not true for water. Water is actually less dense when it freezes. You experience that when you see ice floating, right? Well, why is that? When liquid water, when water is in the liquid state, there's definitely hydrogen bonding, but each of these atoms can twist and turn, and they can move left, right, up, down, front, and back. And so they are experiencing hydrogen bonds, but they are fleeting, right? Because the molecules are still rolling around. When you start to cool it off, right, they start moving around less, and then as it freezes, they're going to freeze in a way that actually maximizes all of that attractive hydrogen bonding. It actually kind of pushes them apart a little bit and explains that interesting density difference when you look at water. Okay, the last section now is going to cover, we're going to skip that. That was just referring back to the insight at the beginning of the chapter. We're going to finish up talking here about liquids. All of these intermolecular forces are at play, but there are a few properties that the intermolecular forces are going to affect. One of them being vapor pressure. So vapor pressure is simply a measure of how much of the gas. It's a measure of the gas phase pressure above the surface of a liquid. So when we look at a liquid, right, so this squiggly line tells you that we're looking at a liquid, right? And you have all of your little molecules down here in the liquid phase, right? There will be some molecules or atoms that escape into the gas phase. And if it is a closed container, those gas phase molecules will condense back into the liquid. Right? You see that here between two different liquids. This is why, an open bottle of water will eventually evaporate and go dry, because those gas molecules escape, but then they leave. They can dissipate into the whole room. Whereas if you have a bottle with a cap on it, then it's not going to evaporate, because you're going to get a dynamic equilibrium. You're going to have molecules going into the gas phase. You're going to have them calming back down and condensing into the liquid phase. You notice some liquids will have more gas, this one over here has more gas molecules above the surface. This one has less. That's going to be the difference between a volatile and non-volatile compound. This one right here would be your volatile compound. It's going to have a higher vapor pressure because there are going to be more molecules in that in that space above the liquid, right? It's a higher pressure because you have more molecules that are hitting the surface of the container and the surface of the liquid. What affects this? Well, intermolecular forces, because why would one substance be able to break into the gas phase more easily than another? Well, it would have lower intermolecular forces. So this particular, property, vapor pressure, is inversely related to intermolecular forces, right? So if you have a high intermolecular force, that's going to lead to a lower vapor pressure, right? And vice versa. Low intermolecular forces would equate to a higher vapor pressure. When we think about boiling point, it's important that we understand the definition. Okay, first of all, normal boiling point is the boiling point occurs when the vapor pressure equals atmospheric pressure. Okay, now, once the vapor pressure, which is going to increase as you are heating a substance, as you are giving more energy to it, more molecules are breaking free and going into the gas phase. Once you get to where that vapor pressure equals atmospheric pressure, then you start to boil. Normal boiling point is going to occur when the atmospheric pressure is at 1 atmosphere. So that is why you can get variable cooking temperatures, cook times for when you're in high altitude regions. Because Water has a normal boiling point of 100 degrees C, but that is at 1 atmosphere. If you go up in the mountains, you have a greatly reduced atmospheric pressure. Water is going to boil at a lower temperature. So if you are trying to cook something, you will have to potentially cook it for more time at a lower temperature, but that's just when the water is boiling. You can see that boiling points, right, are going to be directly connected to intermolecular forces. Higher boiling points go with stronger intermolecular forces. Lower boiling points go with lower intermolecular forces, right? It's all about how much energy it takes to pull those molecules and atoms apart. So vapor pressure and boiling point are going to have an opposite trend, right? If we compare ethane and water, ethane has a huge vapor pressure compared to water, and so water is going to have a much higher boiling point than ethane. The final piece here is surface tension. Surface tension is, we can read this together, right? It's the response to the imbalance in attractive forces at the surface of a liquid, and the atoms at the surface are going to try to minimize that energy. So if we look at this picture here, right, the atoms and molecules under the surface have lots and lots of interactions in all 3 dimensions. But at the surface, these atoms are only going to be attracted to atoms to the sides and below. So there's going to be a little bit of a stronger pull here because they're kind of having to compensate for not having anything above. And so it creates almost like this layer where you have a little bit stronger intermolecular forces. This explains a couple of different things, especially what you see with water, because water has really strong intermolecular forces with hydrogen bonding. It's why water droplets tend to form, right, more of like a spherical shape. It's the water trying to maximize all of those intermolecular forces. It's also why bugs can land on the surface of water, right? So surface tension. Okay. You can even notice this, the difference in surface tension, right? Because this is another one that is directly related. So larger, I realize I'm writing this different every time. Larger intermolecular forces are going to go with higher surface tensions. You can see that if you ever just put a couple droplets of water on a table and then try to put a couple droplets of acetone, water will make a droplet shape, but acetone will just go out flat. Acetone is polar, but it can't hydrogen bond, right? This is acetone. It has oxygen, but there's no hydrogen directly attached to it. So it's got a lower boiling point. It's also not going to give you that same kind of spherical shape. The surface tension, let's go back here. So this isn't in your notes, but cohesive and adhesive forces are important to understand. Cohesive forces are those liquid-liquid interactions. So the water wanting to interact with other water molecules. And adhesive forces would be liquid-solid interactions, be the liquid interacting with the solid. Now, why water will form droplets is because it's usually on a very non-polar surface. So there's more strong interactions to be had with other water molecules. When we look at water in a glass, in this case, graduated cylinder, there's a different adhesive nature here. Because glass has ions in it, there's a lot of polarity in the glass. Water is actually going to be attracted to the glass, and you're going to see that in that concave meniscus shape. The water is actually almost climbing up the glass. It's maximizing those interactions with the glass. When we look at mercury, mercury is just a very nonpolar element, right? It's just a bunch of mercury atoms. There's London forces, but nothing else. The glass is not going to be as attracted to the mercury because the mercury is so nonpolar. So you're going to get more of a convex meniscus where you are maximizing more of those adhesive or cohesive forces, right? Where the mercury just interacts with itself.